There's nothing you need to do right now. Nothing you need to remember. And nowhere you need to be. You may notice that your breathing is already settling into a rhythm of its own, not because you're guiding it, but because there's no need to hold anything in place. Some people notice a soft release in the shoulders, or a sense of ease behind the eyes. Others notice nothing at all. Either way is fine. As we begin tonight, you might imagine looking up into a quiet night sky, not searching, not counting, just noticing that the light you see has been traveling for a very long time. In a moment, we'll begin exploring the science behind how stars age very slowly over immense spans of time. But for now, you can let the words arrive and leave again, remaining only as long as they need to. When we speak of stellar aging, we're talking about timescales so vast they dwarf human comprehension entirely. The process by which a star lives its life and gradually transforms unfolds across millions, billions, sometimes even trillions of years. The most massive stars, burning fierce and bright, race through their existence in just a few million years. For them, aging is almost hurried by cosmic standards. But at the other end of the spectrum lie the red dwarfs, the smallest, coolest, and most patient stars in existence. These modest stellar bodies age so slowly that their lifespans stretch into the trillions of years, far beyond anything we can truly imagine. To put this in perspective, our universe itself is roughly 13.8 billion years old. That sounds ancient, and it is by any measure we use in our daily lives. But in the grand timeline of stellar evolution, 13.8 billion years is still quite young. The universe hasn't been around long enough for even one of those slowest aging red dwarf stars to reach its final stages. Not a single one. They're all still burning quietly, steadily, barely changed from the day they first ignited fusion in their course. They will continue that way for epochs beyond our reckoning. When you look up at the night sky on a clear evening, most of the stars you see are still in what astronomers call the main sequence phase. This is the long, stable period of a star's life when it fuses hydrogen into helium in its core, radiating energy steadily outward. It's the middle chapter of stellar existence, and for many stars, it's by far the longest chapter. The stars you're gazing at tonight are only partway through their evolutionary journeys. They're not young necessarily, but neither are they old. They're simply enduring, as they have for billions of years, and as they will for billions more. As time moves forward, not just through human generations or geological ages, but through cosmic epochs spanning trillions upon trillions of years, the character of the universe will change. The future will belong to those slow-burning red dwarfs. Long after the bright, massive stars have exhausted their fuel and vanished, long after medium-sized stars like our Sun have swelled into red giants and then faded into white dwarfs, the red dwarfs will still be shining. Faint, yes, dim by comparison to the blazing stars of today, but persistent. In those distant eras, the universe will be a quieter, darker place, illuminated primarily by these patient, low-mass stars that refuse to hurry. And even they, eventually, will run out of fuel. Stellar aging is a process of gradual exhaustion. Every star, no matter how long-lived, is slowly consuming the hydrogen at its core. As the eons pass, fewer and fewer stars will remain actively fusing elements. The universe's starlight, once abundant and bright, will gradually dim. Over trillions of years, the night sky will grow darker still as one star after another exhausts its nuclear fuel and quietly fades. What remains after a star dies depends on its mass and its life story. Some stars leave behind white dwarfs, dense remnants no larger than Earth but containing the mass of a sun, glowing faintly with residual heat that will take countless ages to radiate away. Others, more massive in life, collapse into neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons, and the most massive stars of all collapse entirely into black holes, regions of space-time so warped that not even light can escape. In the far future, these remnants will outnumber the bright, actively fusing stars. The universe will be populated mostly by the silent remains of what once shone. It's a slow transformation, gradual, almost imperceptible on any timescale we can observe, but inexorable. The universe is aging just as its stars are aging, and both processes unfold with a patience that stretches beyond all comprehension. Right now, in this moment, the stars are still mostly bright, the universe is still relatively young, and the long, slow dimming is something that will unfold over timescales so distant that they feel almost like abstraction. But it's happening, quietly, constantly, one fusion reaction at a time. stars begin their lives in silence in the cold depths of space where giant molecular clouds drift through the darkness. These clouds are vast beyond imagining, sometimes spanning 100 light years from edge to edge, holding within them millions of times the mass of our Sun in gas and dust. They are nurseries, though nothing about them feels hurried or urgent. Within these clouds, in regions where the gas grows particularly dense, gravity begins its patient work. Slowly, almost imperceptibly, these dense pockets begin to collapse inward under their own weight. This is how a star is born, not in a sudden burst, but in a gradual gathering. As the gas falls inward, drawn by gravity's gentle insistence, something begins to happen. The gravitational energy of all that collapsing material transforms into heat. Not quickly, not all at once, but steadily over hundreds of thousands of years, sometimes longer. The center of this collapsing cloud grows warmer degree by degree as more material piles on top. This embryonic star, this protostar as astronomers call it, begins to glow faintly from the heat of its own contraction. It's not yet performing fusion, not yet burning hydrogen in its core. It's simply radiating the warmth created by gravity pulling everything inward, and so it shines dimly, its energy output changing gradually as it continues to contract. During this time, something else occurs. As material spirals inward toward the growing protostar, it doesn't fall straight down. Conservation of angular momentum ensures that the infalling gas forms a rotating disk around the young star, a flat plane of material spinning in the same direction. From the protostar's poles, jets of material shoot outward, narrow streams of gas propelled by magnetic fields. These disks and jets work together over time, steadily carrying away angular momentum, allowing more material to continue falling onto the star itself. It's a delicate balance, a slow dance that unfolds over eons. There is no single moment when a protostar becomes a star. The journey from collapsing cloud to stable hydrogen-burning star is a gradual transition, a slow fade from one state to another. If you could watch in time-lapse across hundreds of thousands or millions of years, you would see the protostar contracting, warming, gathering mass until finally its core reaches the critical temperature needed for fusion. But there's no sharp switch, no sudden ignition, just a continuous, unhurried transformation. In young star clusters scattered throughout our galaxy, astronomers find stars at various early stages of this process. Some are still protostars, glowing only from contraction. Others have just begun fusion, still others are settling into stable main sequence life. By studying these clusters, observing stars of different ages all born from the same cloud, astronomers can reconstruct how stellar properties change with time. They can watch, in a sense, the aging process unfold, not in a single star over billions of years, but across a population of stars at different life stages. It's like seeing snapshots of childhood, adolescence, and adulthood all at once, and from those snapshots piecing together the story of growing up. through it all, there's a sense of slowness, of processes that unfold over timescales far longer than human civilizations, of changes so gradual they would be invisible to any observer watching in real time. The birth of a star is not a sudden event. It's a patient accumulation, a slow warming, a gentle transition from cloud to protostar to star. And once that transition is complete, the real journey of stellar aging begins. Only when the core of a protostar reaches a temperature of roughly 10 million Kelvin does something fundamental change. At that temperature, hydrogen nuclei moving fast enough begin to overcome their mutual repulsion and fuse together, forming helium and releasing energy in the process. This is nuclear fusion, the process that will power the star for the vast majority of its existence. And once this sustained fusion begins, the star slowly settles onto what astronomers call the main sequence. It has arrived at adulthood, in a sense, and this adulthood will last a very, very long time. On the main sequence, a star does one thing, primarily. It fuses hydrogen into helium in its core. That's it. Hour after hour, year after year, millennium after millennium, the same process continues. 4 hydrogen nuclei combine to make one helium nucleus, releasing energy that works its way outward through the star until it finally radiates into space as light. This is the longest, most stable part of a star's life. In fact, stars spend roughly 90% of their total lifetime in this main sequence phase. For the vast majority of a star's existence, this is what it does. It sits on the main sequence, fusing hydrogen, shining steadily. Our Sun, for instance, has a main sequence lifetime of about 10 billion years. It formed roughly 4.5 billion years ago, which means it's currently about halfway through this stable phase. Halfway through its adulthood, if you will. It has been shining steadily for billions of years already, and it will continue shining steadily for billions of years more before anything dramatic happens. That kind of stability is difficult to comprehend. 10 billion years is a timescale so vast that all of human history, all of recorded civilization, all of the rise and fall of species on Earth represents the tiniest fraction of it. And the Sun, for all its seeming permanence, is actually a relatively fast-aging star compared to some. Low-mass red dwarfs, the smallest stars capable of sustaining fusion, burn their fuel so slowly and so efficiently that they can live for hundreds of billions of years. Some estimates suggest they could live for 1 trillion years or more. The universe simply hasn't existed long enough for us to watch one of these stars grow old. They will outlive everything. They will still be shining long after stars like the Sun have exhausted their fuel and faded away. At the other end of the spectrum are the massive O-type stars, brilliant blue giants dozens of times more massive than the Sun. These stars burn their fuel extremely fast, racing through their hydrogen supply in just a few million years before leaving the main sequence. They live fast and die young by cosmic standards. Their entire lifetime, from birth to explosive death, can be shorter than the time it takes a red dwarf to even finish contracting from a protostar. The relationship between a star's mass and its lifetime is steep and unforgiving. A star's main sequence lifetime decreases dramatically with increasing mass. Double the mass and the lifetime drops by much more than half. This means that two stars born together in the same cloud, siblings in a sense, but of different masses, will reach old age at very different times. The more massive sibling will evolve quickly, perhaps dying in a supernova, while its smaller companion is still calmly fusing hydrogen on the main sequence, barely changed from its youth. Stellar aging is not uniform. It depends entirely on how much mass a star was born with, and that initial mass, determined in those first moments of collapse, sets the clock for everything that follows. For now, though, for the main sequence star, time passes slowly. Fusion continues, light radiates outward. The star shines stable and constant, changing so gradually that the changes are almost imperceptible. Almost. Even during the long, stable main sequence phase, a star is not entirely static. It changes, but the changes are so gradual, so subtle, that they unfold over timescales of billions of years. If you could observe a star for 1,000,000 years, you might notice nothing different at all. But over hundreds of millions of years, over billions of years, the changes accumulate. Here's what happens. As a star fuses hydrogen into helium in its core, the helium doesn't go anywhere. It simply accumulates there, building up slowly as hydrogen is consumed. Helium is heavier than hydrogen, and it doesn't participate in the fusion reactions happening at main sequence temperatures, so it just sits there, inert, gradually increasing in concentration at the star's center. The core becomes more helium-rich over time and less hydrogen-rich. As hydrogen is consumed and helium builds up, the core contracts slightly. It has to. With less hydrogen fuel available, the pressure supporting the core against gravity weakens, and gravity pulls things a bit tighter. This contraction causes the core to heat up. Higher temperature means faster fusion rates in the remaining hydrogen, and faster fusion means the star produces more energy. So, slowly, gradually, over billions of years, the star becomes more luminous. It shines brighter. Our Sun has experienced this. Since it first settled onto the main sequence 4.5 billion years ago, its luminosity has increased by tens of percent. Not a small change, actually, when you think about it. The sun that shone on the early Earth was noticeably dimmer than the sun that shines today, yet the change happened so slowly that Earth's climate systems had time to adapt. Life evolved alongside this gradual brightening, and here we are, still receiving energy from a star that has been steadily getting brighter for eons. Astronomers track these changes using something called the Hertzsprung-Russell diagram, a graph that plots stars based on their luminosity and surface temperature. On this diagram, main sequence stars form a diagonal band stretching from cool, dim red dwarfs at one end to hot, bright blue giants at the other. As a star ages on the main sequence, it drifts slowly on this diagram. It moves upward, becoming more luminous, and it moves slightly to the right, becoming a bit cooler at the surface, even as its core heats up. The movement is slow, imperceptible in human lifetimes, but over billions of years, the star traces a gentle path across the diagram, a record of its gradual aging. Along with changes in luminosity come slight changes in radius and surface temperature. These, in turn, alter the star's color. A young sun was slightly redder than the sun we see today. An old sun, billions of years from now, will be slightly yellower, then eventually much redder as it begins to leave the main sequence entirely. But during the main sequence phase itself, the color changes are subtle. Small shifts in hue that would require instruments to detect, playing out over timescales longer than continents take to drift. This is stellar aging during the long, quiet middle chapter. Not dramatic, not sudden, just a slow accumulation of helium, a gradual contraction, a steady increase in brightness. Changes happening so slowly they seem almost like stillness, but they are happening constantly, inevitably. Even now in our sun, in stars across the galaxy, hydrogen is fusing into helium, cores are slowly contracting, and luminosity is creeping upward. The stars are aging, even when they seem unchanging. Beneath a star's surface, invisible to us but measurable through careful observation, the internal structure evolves as the star ages. The core, where fusion occurs, becomes denser over time, packed more tightly with helium as hydrogen is consumed. This growing helium core changes the way energy moves through the star. In some regions, energy travels outward primarily through radiation, photons bouncing from atom to atom in a slow, random walk that can take thousands of years. In other regions, convection dominates, with hot gas rising, cooling, and sinking in churning currents. As a star ages, the boundaries between these radiative and convective zones can shift. The internal architecture reorganizes itself slowly in response to the changing composition of the core. Young stars, freshly formed from their collapsing clouds, often rotate quickly. They spin rapidly, having retained much of the angular momentum from the cloud they formed from. But as a star ages, its rotation gradually slows. This happens through a process called magnetic braking. The star's magnetic field interacts with charged particles in the stellar wind flowing outward from its surface. This interaction transfers angular momentum away from the star, carried off into space by the wind. Over millions and billions of years, the star spins down, rotating more and more slowly. Slower rotation has consequences. A star's magnetic field is generated by a dynamo process driven in part by rotation and convection. As the star slows down, the dynamo weakens. The magnetic field becomes less intense, and with a weaker magnetic field comes reduced magnetic activity. Young stars are often very active, covered in star spots, flaring frequently, emitting strong X-rays. Old stars are quieter, calmer. Their surfaces are smoother, their flares less frequent, their high energy emissions diminished. Stellar aging brings a kind of settling, a reduction in restlessness. Even the way a star vibrates changes with age. Stars are not perfectly rigid. They oscillate, pulsating in complex patterns as sound waves reverberate through their interiors. These oscillations are subtle, causing tiny variations in brightness and velocity that require sensitive instruments to detect. But they're incredibly useful because the frequencies and patterns of oscillation depend on the star's internal structure. As the core evolves, as zones of different composition and temperature shift, the oscillations change. By studying these stellar vibrations, astronomers can probe what's happening deep inside a star. This field, called asteroseismology, allows us to measure stellar aging indirectly. We can't see the helium accumulating in a star's core, but we can hear the changes in its oscillations and infer what must be happening inside. All of these internal changes, the shifting zones, the slowing rotation, the evolving oscillations, are part of the aging process. They're invisible from the outside mostly. A star looks much the same whether it's rotating quickly or slowly, whether its core is mostly hydrogen or increasingly helium-rich. But the changes are there, unfolding in the hidden interior, altering the star's fundamental character over billions of years. And through careful observation, through measuring rotation rates and oscillation frequencies and magnetic activity, astronomers can track this hidden aging. They can watch a star grow older from the inside out. stellar mass at birth is the main factor determining how slowly or quickly a star ages. This simple truth allows astronomers to use stars as cosmic clocks to measure time on scales far longer than human history. Consider the low-mass stars, those below about half the Sun's mass. These small red dwarfs evolve so slowly that not a single one has yet left the main sequence. Every red dwarf that has ever formed in the history of the universe is still fusing hydrogen in its core. None have aged enough to exhaust their fuel and move on to later stages. They're all still in the prime of life, so to speak, and they will remain there for hundreds of billions of years to come. In a universe only 13.8 billion years old, these stars have barely begun their journey. Medium-mass stars like the Sun evolve on billion-year timescales. A solar mass star will spend about 10 billion years on the main sequence. This is long, certainly, but not impossibly long. We can find stars like the Sun at various stages of their evolution. Some are young, freshly settled onto the main sequence. Others are middle-aged, like our Sun. Still others are old, nearing the end of their hydrogen-burning phase and beginning to transition toward becoming red giants. By studying these stars of similar mass but different ages, astronomers can map out the aging process. High-mass stars, on the other hand, evolve rapidly. They race through their stages, exhausting their fuel in millions rather than billions of years. A star 20 times the mass of the Sun might live only 10 million years before exploding as a supernova. These stars don't have time to age slowly. Everything happens fast for them. This range of timescales gives astronomers a powerful tool. When they observe a star cluster, a group of stars all born at roughly the same time from the same cloud, they can estimate the cluster's age by looking at which stars have already left the main sequence. This is called the main sequence turn-off point. In a young cluster, massive stars are still on the main sequence, burning brightly. In an older cluster, those massive stars are gone, having already exhausted their fuel and died. Only stars of moderate and low mass remain on the main sequence. The more massive the most massive star still on the main sequence, the younger the cluster. As a cluster ages, the turn-off mass decreases. The most massive remaining main sequence stars become progressively smaller. It's like watching a race where the fastest runners finish first. In a young race, everyone is still running. In an older race, the fastest have already crossed the finish line, and only the slower runners remain on the course. By seeing which runners are still going, you can estimate how long the race has been running. Star clusters work the same way. The main sequence turn-off tells you the cluster's age. In this way, star clusters act as cosmic clocks. They preserve a record of time written in the distribution of stars at different evolutionary stages. An astronomer can look at a cluster, identify its turn-off point and say, this cluster is 5 billion years old, or this cluster is 10 billion years old. The stars themselves, through their slow and predictable aging, become markers of cosmic time, and by studying clusters of different ages, we can reconstruct the history of star formation in our galaxy, watching how the process has unfolded over billions of years. Eventually, after billions of years on the main sequence, a star exhausts the hydrogen in its core. Not all at once, not suddenly, but gradually the fuel runs low and the fusion reactions that have powered the star for so long begin to falter. The core can no longer sustain the pressure needed to hold the star up against gravity. And when that happens, the star begins to change in a more noticeable way. With core hydrogen depleted, the star can no longer rely on core hydrogen fusion to support itself. But the star doesn't simply stop shining. Instead, fusion continues in a shell surrounding the now inert helium core. This shell burns hydrogen at its inner edge, converting it to helium and adding to the growing core. It's a new configuration, a new way of generating energy, and it has profound effects on the star's structure. As the hydrogen-burning shell deposits more helium onto the core contracts. It has to. Without fusion to provide pressure, gravity pulls it tighter. This contraction releases gravitational energy, heating the core and the surrounding layers. Meanwhile, the shell fusion produces more energy than core fusion did, because the shell is hotter and denser. All this energy flowing outward pushes on the star's outer layers, causing them to expand. The star grows larger, its radius increasing by tens or hundreds of times. As the outer layers expand, they cool. A larger surface area radiating the same total energy means a lower surface temperature. The star becomes redder. This is how a star becomes a red giant, or if it was very massive to begin with, a red supergiant. The transition doesn't happen overnight. It occurs over millions of years, sometimes hundreds of millions of years, depending on the star's mass. The star gradually swells, its surface cooling and reddening, while deep inside, the core continues to contract and heat up. Our Sun will undergo this transformation in about 5 billion years. Right now, it's still comfortably on the main sequence, with billions of years of hydrogen burning ahead of it. But eventually, the core hydrogen will run out. The core will contract. A hydrogen-burning shell will form, and the Sun will begin to expand, growing into a red giant that may eventually engulf the inner planets, possibly even Earth. All of this will unfold slowly, over timescales longer than Earth has had complex life. But it will happen. It's written into the life cycle of a star like the Sun. Leaving the main sequence is not a sudden departure. It's a gentle transition, a slow shift from one state to another. The star doesn't stop being a star. It simply enters a new phase of life, a phase where the outer layers expand and cool while the core contracts and heats. It's the beginning of the end, in a sense. But even the end, for a star, is a slow process. As the helium core of a red giant continues to contract under its own weight, it grows hotter and denser. Eventually, if the star is massive enough, the core temperature reaches about 100 million Kelvin. At that temperature, helium nuclei themselves can fuse together. 3 helium nuclei combine to form carbon in a process called the triple alpha reaction. And just like that, a new source of energy ignites. The star begins fusing helium in its core. For low-mass stars, this ignition can happen suddenly in what's called a helium flash. The core, degenerate from compression, doesn't respond smoothly to the sudden onset of fusion. Instead, the fusion rate skyrockets for a brief time before settling down. It's a dramatic moment by stellar standards, though still invisible from the outside and over in seconds to hours in the core's frame, even if the energy takes time to reach the surface. After the flash, the star settles into a new stable configuration, fusing helium in its core, while hydrogen continues to burn in a surrounding shell. This helium-burning phase is calmer than the red giant phase that preceded it. The star stabilizes, shrinks slightly, and can spend tens to hundreds of millions of years fusing helium into carbon and oxygen. It's a reprieve, a brief return to stability after the upheaval of leaving the main sequence, but it doesn't last as long as the main sequence phase did. Helium burns faster than hydrogen. The fuel is consumed more quickly. When the helium in the core is finally exhausted, the star is left with a core of carbon and oxygen. For low and medium mass stars, this is as far as fusion goes. Their cores never get hot enough to fuse carbon, so the core simply sits there, inert, while helium fusion continues in a shell above it and hydrogen fusion continues in a shell above that. The star's outer layers, pushed by the energy from these shells, expand again. The star becomes even larger, even redder. It may pulsate, swelling and contracting rhythmically. Stellar winds, driven by pulsations and radiation pressure, begin to carry away the outer layers, peeling them off bit by bit. During this time, convection in the outer layers can dredge up material from deeper inside the star, bringing carbon and other fusion products to the surface. Some stars become carbon stars, with more carbon than oxygen in their atmospheres, glowing with a deep red hue. The surface chemistry changes as the star's interior is mixed and processed. The stellar winds grow stronger. Over tens of thousands of years, they strip away most of the star's outer envelope, casting it into space. This expanding shell of gas, illuminated by the ultraviolet light from the hot core left behind, forms what we call a planetary nebula. Despite the name, it has nothing to do with planets. It's simply a beautiful, glowing shell of gas, the former outer layers of the star drifting outward into space. What remains at the center, after the outer layers have been blown away, is the core. No longer hidden beneath layers of gas, it's now exposed, a dense hot object about the size of Earth but containing a significant fraction of the star's original mass. This is a white dwarf. It's no longer fusing anything. It shines only from the residual heat left over from its previous life, and it will cool slowly over billions and billions of years, fading gradually as it radiates its heat into space. White dwarfs cool so slowly that none have yet had time to cool completely. The universe isn't old enough. Eventually, after trillions of years, a white dwarf will cool to the point where it no longer emits visible light. It will become a black dwarf, a cold, dark cinder floating through space. But no black dwarfs exist yet. Every white dwarf we see is still warm, still glowing faintly, still in the process of that long, slow cooling. They are the future fossils of stars, waiting patiently for the universe to age enough for them to finish fading. Massive stars, those born with much more mass than the Sun, follow a different path. They leave the main sequence quickly, their immense gravity and high core temperatures driving fusion at a furious pace. Once their core hydrogen is exhausted, they don't stop at helium fusion. They keep going. After helium comes carbon fusion, then neon, then oxygen, then silicon. Each stage of fusion produces heavier elements, and each stage is shorter than the last. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, a few thousand years fusing carbon, and only a few days fusing silicon. The progression accelerates, the star racing through its late stages in a cascade of fusion reactions. Finally, the core produces iron, and iron is where fusion stops. Fusing iron doesn't release energy, it costs energy. So when a massive star's core fills with iron, there's no more fuel to burn. the core can no longer support itself. And once the iron core reaches a critical mass, about 1.4 times the mass of the Sun, it collapses. The collapse is catastrophic and nearly instantaneous. In less than a second, the core implodes, compressing to incredible densities. The infalling material rebounds off the ultra-dense core, sending a shockwave racing outward through the star. This shockwave, combined with a flood of neutrinos from the core, blows the star apart in a supernova explosion. The entire star, except for the core, is flung into space at a significant fraction of the speed of light. The explosion is bright, unimaginably bright. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. And in that explosion, elements heavier than iron are created, forged in the intense heat and neutron flux of the blast. Gold, platinum, uranium, all the heavy elements we find in the universe were made in supernova. The explosion enriches the surrounding space with these elements, mixing them into the gas and dust that will eventually form new stars and planets. What's left behind at the center of the explosion is the core. If the original star was massive enough but not too massive, the core becomes a neutron star, an object so dense that protons and electrons have been crushed together into neutrons. A neutron star might be only 20 kilometers across, yet it contains more mass than the Sun. If the original star was extremely massive, even a neutron star can't support the core. It collapses further into a black hole, a region where gravity is so strong that space-time itself is warped beyond repair. Massive stars live fast. They burn bright and they die explosively in events that reshape the galaxy around them. But even their deaths are part of the slow cosmic cycle of stellar aging, part of the process by which the universe recycles its material and creates the elements necessary for planets and life. Aging stars don't just change themselves, they change the environments around them, including any planets that might orbit them. As a star slowly becomes more luminous during its main sequence life, the amount of radiation reaching its planets increases. Over geologic timescales, this can alter planetary climates in profound ways. A planet that was comfortably warm a billion years ago might be scorching hot today, its oceans evaporated, its atmosphere stripped away by the increased energy from its aging star. Earth itself has experienced this gradual brightening of the sun, though our planet's climate systems, the carbonate-silicate cycle, plate tectonics, and the evolution of life itself have helped regulate temperatures and keep the planet habitable. When a star finally leaves the main sequence and becomes a red giant, the consequences for any inner planets can be dramatic. The expanding outer layers of the star can engulf nearby worlds entirely. Mercury, Venus, possibly even Earth may be swallowed when the Sun becomes a red giant billions of years from now. These planets won't survive the encounter. They'll be vaporized, their material mixed into the star's outer envelope, leaving no trace behind. Meanwhile, as stars age, and especially as they reach their late stages, they shed material into space. Stellar winds from red giants, the ejected envelopes of planetary nebulae, the explosive debris of supernovae, all of this gas and dust mixes into the interstellar medium. It enriches the galaxy with heavier elements, elements that didn't exist when the universe was young. The very first stars had almost no heavy elements. They were made of hydrogen and helium, the primordial elements from the Big Bang. But when those stars aged and died, they released carbon, oxygen, silicon, iron, and more into space. Subsequent generations of stars formed from gas that was enriched by the deaths of earlier stars. Supernova, in particular, are crucial for this enrichment. When a massive star explodes, it doesn't just spread existing elements. It creates new ones, elements that can only be forged in the intense conditions of the blast, and the shock wave from the supernova can trigger new star formation, compressing nearby gas clouds and causing them to collapse. In this way, stellar aging and death directly lead to the birth of new stars. The cycle continues. The elements in planets, in our bodies, in everything around us, originated in aging stars. Carbon, nitrogen, oxygen, the building blocks of life, were made in the cores of stars that lived and died before the sun was born. Iron in our blood was forged in a supernova. Gold in jewelry came from the collision of neutron stars or the explosive death of massive stars. We are, quite literally, made of stardust, the processed remnants of stars that aged slowly over billions of years and then released their contents into the cosmos. Repeated cycles of star formation, aging, and death have enriched galaxies over time. Early galaxies were metal poor, their stars made mostly of hydrogen and helium. Modern galaxies, after billions of years and countless generations of stars, are metal-rich with enough heavy elements to form rocky planets and support complex chemistry. Stellar aging over cosmic timescales has made the universe a more chemically diverse place, and that diversity has made planets and life possible. Our understanding of stellar aging comes from observation, from careful measurements of light and motion and vibration, from studying populations of stars at different stages of their lives. One of the most important tools is the Hertzsprung-Russell diagram, the graph that plots stars by their luminosity and temperature. On this diagram, stars of different ages occupy different regions. Main sequence stars form a diagonal band. Red giants cluster in the upper right, cool but luminous. White dwarfs sit in the lower left, hot but dim. By placing a star on this diagram, astronomers can infer its evolutionary stage. Young star clusters contain massive, short-lived stars still on the main sequence. These clusters are bright, dominated by hot blue stars. Older clusters lack these short-lived stars. The massive stars have already exhausted their fuel and died, leaving behind only stars of lower mass, still slowly working through their hydrogen. The cluster's color shifts redder with age as the blue stars disappear. Within older clusters, additional features appear. A red giant branch, where stars that have left the main sequence swell into giants. A horizontal branch, where stars are burning helium in their cores. These branches mark late stages of stellar evolution, stages that only appear after billions of years. By studying the distribution of stars along these branches, astronomers can refine their understanding of how stars age. There are other clues. Gyrochronology uses a star's rotation rate to estimate its age. Young stars spin fast. Old stars spin slowly. By measuring rotation and comparing it to models of magnetic braking, astronomers can estimate how long the star has been slowing down. Similarly, activity indicators, things like star spot coverage, flare frequency, and X-ray emission, decline with age. A very active star is likely young. A quiet star is likely old. White dwarf cooling sequences act as cosmic clocks in their own right. Since white dwarfs simply cool over time, their temperature tells you how long they've been cooling. The coolest, dimmest white dwarfs are the oldest. By measuring the temperature distribution of white dwarfs in a cluster or a region of the galaxy, astronomers can estimate the age of that population. Even a star's chemical composition, its metallicity, affects how it evolves. Stars with more heavy elements evolve slightly differently than stars with fewer heavy elements. By measuring metallicity and comparing it to models, astronomers can trace stellar evolution across different environments and different epochs of the galaxy's history. galactic surveys, large projects that measure the properties of millions of stars across the Milky Way, reveal age gradients and patterns of star formation. The central regions of the galaxy tend to have older stars. The spiral arms have younger stars. The halo, the diffuse region surrounding the galaxy, contains some of the oldest stars known, relics from the galaxy's early history. By mapping ages across the galaxy, astronomers can reconstruct how the Milky Way formed and evolved over billions of years. All of this, the diagrams, the measurements, the surveys, comes together to give us a picture of stellar aging. We can't watch a single star grow old. The timescales are too long. But we can observe stars at every stage, compare them, model them, and piece together the story of how stars change over time. And from that story, we learn not just about stars, but about the universe itself, about time, about the cycles of creation and destruction that have shaped everything we see. Some of the stars we see in the night sky as red giants today were ordinary main sequence stars, much like the sun when dinosaurs walked the Earth. They've been aging throughout the entire span of complex life on our planet, slowly swelling, slowly brightening, slowly transitioning from one phase to another. And yet to us they appear unchanging. We see them as they are in this moment, frozen snapshots in a process that spans eons. The sun's slow aging has provided something precious, stability. For billions of years, its luminosity has increased, yes, but gradually enough that Earth's climate could adapt, that life could evolve and thrive. If the sun aged quickly, if it brightened dramatically in mere millions of years, life as we know it might never have had time to develop. But stellar aging for a star like the Sun is slow enough to allow for complexity, for evolution, for the emergence of intelligence. We exist because our star ages slowly. Stellar aging also determines the availability of elements for planets. The first stars, made of only hydrogen and helium, could not have formed rocky planets. There was no silicon, no iron, no carbon or oxygen in significant amounts. Only after generations of stars aged and died, enriching the galaxy with heavier elements, could planets like Earth form. Our existence depends on the deaths of earlier stars, on the slow accumulation of heavy elements over cosmic time. Most of the stars visible in the night sky tonight are only partway through their lives. Their main sequence stars, calmly fusing hydrogen, aging imperceptibly. They will continue for billions of years more, changing so slowly that entire civilizations could rise and fall without noticing any difference in the stars above. Stellar aging operates on a timescale that dwarfs human experience, a timescale that reminds us how brief our moment is in the vast flow of cosmic time. Understanding stellar aging links stars, planets, and life together in a single story. It shows us that we are not separate from the universe, but woven into it, made of its material, shaped by its processes, emerging from billions of years of slow cosmic evolution. The stars age slowly, patiently, transforming themselves and enriching the galaxy in the process. And in doing so, they make everything else possible.